Hi everyone, welcome back. So in this video I'm going to do an AC analysis of a common emitter transistor amplifier but with a collector feedback. As you can see, RF here. It's actually taking a portion of IO into IB. Alright. So this is an AC analysis. So the steps for AC analysis has always been you short all capacitors. So that's C1 and C2 there, and you short them because they'll have very low impedance. We assume they have very low impedance at the frequency of interest. We zero all DC sources, which in this case has only one, VCC. Finally, we replace the transistor that's here with an RE model. So just a reminder, RE model is this is the RE model. All right. Okay, so that's the RE model. So there's a beta IB beta RE at the base, between the base and emitter, and there's a beta IB dependent current source between collector and emitter. All right. So so just as an analysis of what we do here, so C1 and C2 will be short, so it'll just be a straight line here going to VI and a straight line here going to VO. When you zero all DC sources, in this case you just have a VCC, so when this goes to ground, so that means VC becomes 0 volts, so it goes to ground. That means RC, one side of RC will be connected to the collector, right? And then the other side of RC will be connected to ground. So that top part of RC will end up ground. That means be connected to the emitter side. All right. So the odd thing is this RF, where it actually sits between. If you look at this, between base and collector. So this is base. So that's collector. So RF will sit in between here, right? So RF is going to sit in between there. Okay, so once you do all that, short this, turn that into 0, and then replace the transistor with the RE model, you should be able to get a model, an AC equivalent circuit that looks like this. All right. So let me explain. As I mentioned just now, RF will straddle between base and collector, like so. All right. Again, if you look at the as per usual, we need to label all currents and voltages. So you still have your VI there. Yeah, VI is between base. Yeah, this becomes a short, so between base and ground. So there it is. That's base, and this is ground. VO will be one end will be at the collector, the other end will be at ground. So that's VO. That's the collector side. So top part of VO is connected to the collector side, and the other side is connected to ground. RC, one side of RC will be connected to the collector, and the other side of RC will be grounded because of the zero of all DC sources step. So RC will come down. So you have the top part of RC ends up ground. So it's going to come down here. So connected to all the ground. All right. So then you have beta IB. This just will still be there. So between collector and base. So there it is. That's beta IB between collector and base. So this is the base part, right? The base part is where beta RE and at the bottom of beta IB shares a common node, which is ground, given here. All right. All right. So we need to derive the usual 4 terms. All right. And I think the first thing we need to do is just to derive some equations that we see here. So for example, we have an IO. IO is a current that flows through the load resistor, if you like. So in this case, it's just RC because there's no RL here. Of course, if there is an RL, then it will be parallel to RC. You'll have an RL here as well if there is an RL. So there is not an RL here. So what's left is just RC. So IO is the current that flows through the so-called load resistor, which is just going to be the collector resistor. So that's I0. So this part here is just beta IB, which is also, of course, is IC. And then on the other side, the current that flows through beta RE will always be IB. you have an II that's going into the base terminal, and then I've labeled a current IF. All right, I've labeled a current IF, which is a current that flows through RF. All right, it flows through RF, the feedback resistor. All right. So first, you need to come up with a set of equations that, well, as many set of equations as you can, so that might help you to figure things out. So let's just derive some equations here. So the first equation I'm going to put is I think relating IO, IF, and beta IB. If you look at this, IO is IF plus beta IB. So beta IB is coming down here. IF is going across. So IO is just those two added together. So so I'm just going to type here generating a few equations. Generating equations. All right. So we're going to have the first one. We're going to have IO. All right, is going to be equal to IF plus beta IB plus beta IB. All right, so that's first equation. All right, now additionally, if you look at IF and you look at RF, if you notice, the right side of RF is actually VO, and the left side of RF is actually VI. So another expression you can write. I'll write here. So you can relate what IF is. All right. So you're gonna say IF is base I equals V over R. So V over R. The V here is gonna be VO minus VI. Right. It's gonna be VO minus VI. That's our voltage across RF divided by I equals V over R, so divided by R, which is RF. All right, so that's another equation. So IF is equal to that. So some more equations that you can write. You can write about VO, for example. You know, so VO here, VO is sorry, VI rather. So VI is over here. You can write an equation for VI, which is simply I equals V over R. Sorry, V equals IR. So that's IB going into beta RE. So you can write an equation for that as well. So V underscore I is equal to V equals IR. So that's IB. That's the current through beta RE multiplied by beta RE. All right. So that's another equation about that we can write about VI. We can also write an equation about VO, because if you notice here, VO is a voltage across RC. All right, so you can write an equation for that relates to VO. So VO is going to be equal to well, if you look at VO, the IO is actually pointing up, so it has to be a negative IO. All right, multiplied by RC. So it's just standard Ohm's law. All right, so it's just standard Ohm's law. So we now have a bunch of equations here that we can play with in order to eventually come up with an answer for the four items, the four usual items that we have when we do AC analysis. All right, so the first thing that I'd like to try is I'm going to try a ZO first. All right, so if I look at ZO, because I think it's probably the easiest. So if you look at ZO, ZO is pointing towards there, and as always, when you're working out the output impedance, you must always zero the source. All right. Okay, so so for ZO, we must zero the source, which in this case is simply VI. Oops, sorry, VI. Okay. So therefore, you're going to get, well, what happens? Well, when VI is zeroed, the top of beta RE and the bottom of beta RE will be at the same potential because this becomes 0 volts. So ground is already 0 volts. So if this is 0 volts, that means both top and bottom of beta RE will be 0 volts. So that means there is no potential difference, which means there is no IB. So IB would be 0, no current. So if IB is 0, then you're going to get beta IB also 0. All right, so you can get IB 0, beta IB 0, and since the top part becomes ground, beta RE will disappear because, well, obviously because top and bottom are at the same potential. But now you'll notice that RF, the left side of RF will also end up at ground. So now you're going to have a situation where you look through ZO from the right, you're going to see, well, the beta IB will disappear, yeah, because IB is 0. Beta RE will disappear because both top and bottom of beta RE will be at 0 volts, so that's going to go. But now the left side of RF is also 0, and then the right side of RF is sharing with the top of RC, meaning that RC and RF will now be in parallel. So the immediate equation that we can write for ZO, all right, is simply equals to RF parallel with RC. All right. So that's our answer for ZO. So ZO is pretty easy. Okay. Okay. So now let's have a look at other areas, other components. So let's have a look at ZI, for example. All right. So ZI, well, we can look at it as VI over II, right? So ZI is just VI over I. So again, just Ohm's law. All right. So for ZI, using Ohm's law, so you're just gonna get ZI is simply VI divided by II. All right. Okay. So now, if you look at II, well, if you look at II here, you have going into the base node, you have an II going this way, an IB coming down, and an IF going that way. So actually, you can actually write an equation that relates II, IB, and IF. So I think I'll write it up here. So I'll just add another equation here. So this one, I mean, what is the equation here? Well, well, it means that IB must equal to II plus IF, right? So IB is coming down, so it must be this plus that to equal that IB. So I'm going to write that IB, well, IB is equal to II plus IF, or I can write simply II is equal to IB minus IF, right? All right, so I can write II is equal to IB minus IF. Okay, so now that we have II, so we can expand it here. So we're going to try and expand it here. All right. Before we do that, I think we need to expand what II is because we need to substitute IF from various places here. So for example, I could put this IF term here. I could dunk it into this. All right, so that I have in terms of IO. All right, or I could, for example, take VI and VO and substitute into here. All right, I could do that too. So there's a few ways of doing this. So what I'm going to do is I'm going to use a way to figure out what IF is. All right, by expanding this term IF here. All right, so before we get to ZI here, I think we need to do some expansion of IF. All right, so let's do that later. So let's continue expanding IF. All right, So we're going to have IF, because IF is equal to VO. Well, let me just copy that. All right, so IF is equal to all of this. All right, which is now where now I'm going to replace VO with all of this. So we're going to have a negative IO negative IO RC. All right, that's the VO part. Sorry, this is RC. All right, that's the VO part, and then it's a minus VI. VI is IB times beta RE. All right, so I'll put all this in bracket because we need to divide all this by RF. All right. So now I'm going to substitute IO. Well, IO has IF plus beta IB into this IO part, so that I get rid of the IO component. All right. So let me just copy this, paste it here, and then for IO, I'm going to expand it. This is IO, right? So this IO here, I'm going to expand it. All right. So IO inside here is going to become IF. I'll just copy this. All right. So it's just going to be this. That's what IO is. So I'm going to copy it and put it there. All right. So negative IO becomes negative IF plus beta IB times RC minus IB beta RE divided by RF. All right. So now I have a term here that has IF on one side and IF also on the other side. All right. So I'm going to continue with this line of equation. All right. So here we're going to say I'm going to put RF on the other side, so it becomes IF times RF. So IF times RF is going to be equal to, so this RF I've put across to the other side, and it's going to be equal to all of this, right? It's going to be equal to all of this. So okay, it's going to be equal to all of that. All right. Okay, so now I'm going to collect IF together. All right, so this is going to be IF RF. Okay, so this is going to be, well, okay, let me just write it out first. So this is going to be negative IF times RC. All right, negative IF times RC. And then so negative, and so minus plus, it becomes negative beta IB times RC. All right, so that's that bracket expanded, and then minus IB and beta RE. All right, so now I have it in those terms. So I think I'm going to use the horizontal space here, so that, well, let me just put it down first, and then I'll bring it up a little later. All right, so I can collect all the IF together. So we're going to have IF here. All right, so you're going to have RF, and this negative IF RC will just go to the left, so it becomes plus IF RC. So when I factor out IF, then I'll take that out. All right, and that's going to equal to well, okay, there's a common here. That's beta IB, negative beta IB for that is. So I can do a negative beta IB. All right, so all right, and then in brackets it's going to be RC plus little RE. All right, okay. So then finally I can now collect. I can now write in terms of just IF. So therefore IF is going to be equal to all of this All right, all of that, all of that. I think I'm well divided by RF plus RC. All right, so that's what IF is going to be. All right, so now I have an expression for IF that I can then use in places where I need to in order to solve for equations. So let me just put all this. Okay, just put all into one line so that I save some space. All right. Then I'll do a double arrow here to mean it becomes that. So all right. Oh, that's a bit big. Okay. Okay, let's just say that. All right, so that's going to be that. And then this becomes this. All right, and then finally we have an IF that is equal to all of this. All right, so that's how I managed to get IF. All right. Okay, so coming back to our ZI. All right, so coming back to our ZI, we can actually impedance, that is. So we can actually say, you know, VI over II. So what is VI? We have this, that's VI. All right, so we put that there. All of that divided by II. Well, what is II? II is IB minus IF. Well, IB minus IF is just IB. So sorry, brackets here. IB minus IF. Well, I have an IF now, so this is my IF. All right, so that's my IF. So minus, negative, all of that. All right. Okay, it's going to be kind of small. Oh, sorry, I need to close the bracket here. All right. All right. So, which is going to be equal to, you know, if I were to, because there's IB at the bottom, so there's IB here and there's also IB inside here. So actually, I can factor out IB. So the top part would be IB beta RE, all divided by, okay, so I'm going to take IB out as a common factor. Oh, sorry. All right, so IB as a common factor. All right, so once I take out IB, this minus minus becomes a plus. So it becomes IB multiplied by 1 plus, all right, 1 plus is going to be almost everything here except for IB, of course. So it's going to be all of that except for IB because we're factoring out IB. So IB would be outside. All right, so I'll just have this. And then all right, so close that bracket. And then close one more bracket. And that's what we have. So so obviously from here we know that IB and IB can cancel. Okay, so II is IB minus, yeah, correct, IB minus IF. IF is all of this. All right, and then okay, so let's just expand that. So all right, so IB can then cancel out. So this IB, this IB, and that IB at the bottom will cancel out. All right. So then you're left with beta RE. All right, so it's going to be left with, well, it's going to be all of this, except for IB, of course. All right, so it's just that there's no IB. All right. Okay. Well, we can try and simplify this a bit. For example, all right. So for example, you can say that, well, since RE is typically very small compared to RC, all right. So RE is very small compared to RC. Then you can write it as beta RE divided by 1 plus beta RC divided by RF plus RC. All right. So that's one way of simplifying it. Okay, that's one way of simplifying it. So I'm going to leave it at this for Zi. Okay. All right. So moving on, we have now trying to look for. So we now have a ZO, an expression for ZO, and an expression for Zi. So it looks a bit complicated, but that's how it is. So now let's have a look at AV. Do we have enough information? Well, AV will be, it can be VO over VI, and IO you can express in terms of, well, here, IF plus beta IB. And since we know what IF is, so we can actually go and figure out what AV should be. So let's figure that out next. For AV, all right, then basically it's just simply AV is equal to VO over VI. All right. Okay, so VO, we know it's negative IORC. All right, which if you can see here, I've already done an expansion here. So VO is equal to negative IORC, and then that got expanded to all of this. So I'm going to use this as my VO. All right, so I'm going to use this as my VO. So I'm going to copy that. All right, so that's going to be my VO. All right, so that's my VO. All divided by VI. Well, VI is IB beta RE, so I'm going to copy that. Put it there. All right. So space. So so now I have it in this way. And of course, next thing is I want to expand IF. So I'm going to replace IF with this term here. So this is what we found for IF. All right. So therefore, this is going to be equal to, that's negative in front. All right. And then at the top is going to be IF there. All right. So that's going to be IF. So that's IF plus beta IB. All right, that's beta IB. All of this is multiplied by RC, and all of this is then divided by IB and beta RE. All right. Okay, right. So I can take beta IB as a common factor up there, and I'm just going to reverse because this is a negative, so I'm just going to say it's going to be beta IB minus all of this. So I'll still have that negative on the outside, the initial negative there. And then I'm going to have a beta IB as a factor, and then in brackets going to be 1 minus, the 1 here refers to this here, so beta IB beta IB times 1, that will get me the positive, and then minus this part here. So it's going to be minus RC plus RE, all divided by RF plus RC. All right, and then all of this is then multiplied by RC there. So close bracket and multiply by RC. All right, so that's the top part, and then all of this is then divided by beta IB RE. So beta IB RE. All right. All right. So so then beta IB cancels out. So I can cancel out beta IB both top and bottom. Okay. So and then I can simplify the top term there. Okay. So now that the beta IB cancels out, so I'm going to expand this. So this 1, I'm going to turn it into an RF plus RC minus RC plus RE. All right, so you still have that negative in front. So then you're going to have RF plus RC, all right, minus RC and minus RE. All right, so RF plus RC becomes here. The 1 becomes RF plus RC divided by RF plus RC, basically. All right, so then the top part becomes this, and the bottom part becomes RF plus RC. All right. Okay, and then all of this is multiplied by RC. Okay. If you notice here, there's an RE here, so I can actually write like this: multiply by RC divided by RE. All right. So then I have this term there. All right. So this RC and this RC will cancel out. So then you're left with at the top there RF minus little RE. All right. This one is divided by RF plus RC. Oops, sorry. Let's put a bracket. So bracket RF plus RC. All right, and of course you still have that. You still have that RC divided by little RE. All right. Okay. Okay, so that's the expression for AV. So we can simplify it a little bit further by saying things like RE is typically very small compared to RF. So then the top part will just be left with just RF. So then you just have a RF over RF plus RC, and if RC is much smaller than RF, then you're just going to have RF over RF. That cancels out. Then what's left is just RC over negative RC over RE. All right, so let's just capture that on the next line. So therefore, AV, which is our voltage gain, is going to be. Oh, okay. Let's make some assumption. Assuming that number one assumption is we're saying that RE is very much smaller than RF. That's number one. So it should be at least 10 times smaller than RF. Okay. Okay, and another assumption that we can make is that RC is typically much smaller than RF as well. Okay, so if we can make those assumptions that RC is much smaller than RF, so at least 10 times smaller, sorry, RF. All right. So then you can write AV as equal to, okay, so if RE is very much smaller than RF, that means this RE will disappear. So you just have with negative RF over RF plus RC. All right. But then if RC is even much lesser than RF, then basically you're just going to be left with, so the RC will be insignificant. So then you just left with RF over RF, which cancels out. So then what you're left with is just negative RC divided by RE. All right. So that's our AV approximation given these conditions. All right. So we have ZO, we have ZI, AV. So finally, let's work out what AI is. All right. So for AI, that's the current gain. It's just going to be I/O. By definition, it's just going to be I/O divided by II. All right. So we have we obviously have some expressions for I/O and II. So for example, I/O is, if you look at the top here, I/O is equal to IF plus beta IB. All right. And then furthermore, IF is all of this. So let's just do that step by step. So I/O is just going to be this, right? So put in bracket all of this divided by II. What is II? Yes, II is, have we done an II here? Well, there is an II here. I mean, from here, you know, II is IB minus IF, all right? And then by substituting IF, which we've done here, into this, you get this expression here, all right? You get this expression here. So I'm gonna, okay, so I'm just gonna take this expression here because in this case I've factored out IB, so then it becomes this. So I'm gonna take that as my expression for II, all right? So that's gonna be my II, all right? Okay, that's for II at the bottom, all right? At the top, I need to expand as well. So this one, there's no, we're not canceling yet. So let me remove this highlight. So remove that highlight. All right. So so the top part is I have a IF plus beta IB, which is, if you look, is this term here. All right. So which eventually ends up as this term here, right? So this term here multiplied by RC ends up as this whole thing here multiplied by RC. So I'm just going to take this part here, beta IB times all of this times RC. So that's going to be the next thing that the top part is going to be equal to. All right, so the top part of IF plus beta IB, I have done it here already. That's this term here, IF plus beta IB. So I plus beta IB, when I expand it, because it's times RC, just simply becomes all of this. So I'm just going to copy this. All right, that's what it becomes. So that's going to be the equals to, so that's going to be equal to the top part, which is that, divided by the bottom part, which is this. Oh, yeah, which is this. All right, so I'm going to copy that and put it over here. All right, so open, close, place, space. Yes. All right. So so the highlight is obviously not because we can't cancel out everything. So the only thing we cancel out is actually IB. So that's what I'm going to highlight to mean that IB now disappears, cancels out. All right. So now I have this rather cumbersome looking expression. So let's just continue to simplify it. So that's just equal to, well, it's going to be, okay, so what I'm going to do now is I'm going to expand this RF plus RC into this one, all right, and basically I'll end up like here, because I've already done it up there. Actually, I've already done it here. So this is going to be RF minus RE, except for the beta. The beta will still be there. So it's going to be beta, all right, and then multiply by RF minus little RE. So that's what the top part will simplify to. And all that is going to be divided by, all right, so here I'm going to also simplify it a little bit, all right, in the sense that this is going to be RF plus RC over here. All right, so let me just do that. So divided by, so it's going to be RF plus RC. So remember, yeah, even the numerator has an RF plus RC in its denominator. So basically, the RF plus RC of both top and bottom will disappear. All right, we'll cancel each other out. Okay, then plus beta RC plus RE. So I'm going to write beta RC plus beta RE. All right, so plus beta RE. So I'm just expanding out beta in this term here. All right. Okay, so I have that now. So I can then again factor out. I can factor out. I can either factor out beta. All right. So let's factor out beta here. So everything's going to be the same, except for the fact that the bottom part will have a beta that's so it's going to be RC plus RE. All right. So it's going to be RC plus RE. Okay, so that is our expression for AI if we don't simplify much. However, I can simplify it further by saying things like a similar assumption that I've made earlier, assuming that RE is much smaller than RF. All right, and even RC is much less much less smaller than. Well, let me just do it one step at a time. Okay, let's say assuming that RE is much smaller than RF, so then my AI, all right, is going to equal to, so the top part, okay, so we're talking about RE much smaller than RF, so that means I can even assume, oh, okay, so that's one more thing. Let's say RE is much smaller than RF, and RE is also much smaller than RC. All right, so then AI, if so, that means RE is much smaller than RF, which means this term will disappear, and if it's much smaller than RC, then this term will disappear. All right, so then our expression is going to look like beta at the top there, beta RF, all divided by RF plus RC. Those guys are still there. All right. Now, since RE disappears compared to small compared to RC, so you're left with just beta RC. All right. All right. So I can make RC common down there. So then I'll just have RC multiplied by beta plus 1. All right, RC multiplied by beta plus 1. And of course, another assumption I can make is since beta is much bigger than 1, then you're just left with the following expression. So now if we continue with again assuming a full stop. Now if you further assume, maybe I'll just hang on. Let me just simplify the bottom part first. So the top part is going to be beta RF all divided by, so if I were to simplify the bottom part by factoring out RC, so it's going to be RF plus RC, oops, bracket beta plus 1. Alright, so that's what's going to become, and of course I can assume beta is usually much bigger than 1, so then I'll just have beta RF divided by RF plus beta RC. Alright, so assuming beta is much bigger than 1, alright, then I can write that AI is going to equal to beta RF all divided by bracket RF plus beta RC. Alright, okay, so I think I'm going to try and simplify. AI I'm going to leave it at this, but for ZI I think I want to simplify this a bit more. Right. So what I can do now, I could leave it like that, or I could, something that's in your notes. I could divide both top and bottom by beta. So if I do that, so I'm going to get RE at the top, all right, divided by 1 over beta plus, all right, so since I'm dividing everything by beta, this beta will disappear. So then what I have here is it'll be RC plus RE, all right, all divided by RF plus RC. Close bracket, space. All right, so I get this. Now, I could leave it at this, or the other assumption I could make is little RE is usually much smaller than big RC, and the other one is RC is actually usually much smaller than RF. All right, so I could end up with the assumption. Based on that assumption, I could then rewrite this in a slightly different way. All right, so maybe I'll just say assuming. So I'm going to run out of space here. Assuming that RE is much smaller than RC. Okay, and another one is RC is much smaller than RF. All right, so if I have those two assumptions, then okay, maybe I'll put this on the next line. All right, so I'll put this on the next line. Assuming that all this is true, then I can write for ZI. So ZI is going to be equal to RE all divided by 1 over beta, that's still there, plus, well, if RE is much smaller than RC, all I'm going to have is just RC at the top, divided by, if RC is much smaller than RF, just RF, right? And that's it. So that's my That's my simplified version of Zi. Okay, it's running out of space here, so let me just adjust the size a bit so that I can try and fit everything onto one screen. Well, I'm just going to pull this down a bit more because I have a whole bunch here. So I'm just going to highlight the expressions that matter. All right, so in a different color. So for example, this is ZO, so I'm going to highlight it with a green color. So that's one answer. The other answer is about ZI. That's this answer. And then there is an expression about AV, of course, after that, after several assumptions. And finally, an expression for AI. All right, so there, now I have all four terms. Okay, so see you guys in the next video. Thanks.